One-sided limits will often look at piecewise functions, and we're going to be looking at limits coming either from the left or from the right. So if you copy down this notation that you see here, you'll see a limit with a little negative sign up top versus a positive sign. The negative means limit from the left. And the little positive sign, so just these little signs up here, the positive means looking at the limit coming from the right. We actually looked at this on the first day when we looked at things graphically. We made sure that the left and right side were the same. They're approaching the same thing, and then we said what the limit was based off of that. Our theorem that kind of goes along with that says the limit as x approaches c of some function exists if and only if, remember, if and only if means you can take this statement and go either direction. The limit as x approaches c from the left is equal to the limit as x approaches c from the right. Or in words, the left-sided limit must equal the right-sided limit. Okay, so we're going to be taking a look at either left or right side or both. Especially in piecewise functions, we want to make sure that the left and the right side are equal to each other. The first example we're actually going to look at is the radical function. So kind of picking up where we left off in our last lesson, we had looked at radical function and the domain of that function. So if we look at the domain of this, we think about this graphically. It starts at 4 and goes to the right. So our domain is x is greater than or equal to 4. What that means is we can't evaluate from both sides at 4 because there's only one side to this graph. And when we're talking about that, we're talking about the limit as x approaches 4 of this function. Since the domain is either 4 to infinity, if you'd rather that notation, or x is greater than or equal to 4, we can't approach from the left side. Okay, so if you were asked, does a limit as x approaches 4 of the square root of x minus 4 exist, you would actually have to split this into two parts. You would have to find the left-sided limit and the right-sided limit. The left side limit does not exist, so we'll put D and E for does not exist. And you might not recognize that without thinking about the domain first, because you might just think, I'll just plug in 4 and I'll get my answer. That's not going to be the case here. You do have to think about this and what would happen graphically with this particular function. So be very careful whenever you see the square root functions, not to just go plug things in right away, even though when we talked about algebraically, that was our first step. You do also want to think about the domains of these functions. Here, since we can approach from the right, we know we have a domain on that side. We can plug in the 4 and get the limit of 0. So since we have the domain on the right side, you can plug in the value. We don't have the domain on the left side, so that would be a does not exist. So that's a specific example that you'll want to review. And there's another one at the end of this lesson that we'll also want to take into account. Okay, so now let's take a look at some piecewise functions and how we will work with those. Our first example, f of x, is equal to 4 minus x if x is less than 1, and 4x minus x squared if x is greater than 1. This only has 2 parts. So when we have 2 parts, we can say, okay, this part is the left side, and this is the right side of 1. And we could graph this to see what's happening, but let's try not to do that. We can look at our inequalities and see that less than means left, greater than means to the right. So if you're then asked some questions about limits, limit as x approaches 1 from the left, we'll also do the limit as x approaches 1 from the right of the function. Compare those two answers to then say what the limit as x approaches 1 of the function will be. And you're actually going to notice that most of the times the limits will match up with the inequalities that are over here. So if I'm doing this from the left, I want to show that I'm plugging into the left side of the equation. That's going to give me 3. There's not a lot of work to show here, but you do want to show this work. And then if I have the plus sign, that means from the right side. So I'm going to plug into the second equation, the one that's coming from the right. I also get 3 for that. Since those are the same, they're approaching the same value. If we go back and look at my original theorem, limit as x approaches c of f of x exists if and only if the left side limit equals the right side limit. So since the left and right side are equal to each other, the limit as x approaches 1 is also equal to 3. You don't need to show any work for that. You just want to look and see if those first two are the same. Now, it gets a little trickier when we have multiple functions, 3 or more. So I'm going to do a nice big example that has a lot of functions for this one. Since this one's a little bit long, we'll make this our last example for our first video for the one-sided limits. This is a good one because it has a lot of different scenarios happening in it. All right, so I'm going to separate this into like an A, B, C, but there's going to be multiple parts in my part A, but they all kind of go together. So limit as x approaches 1 from the right. Then I'm going to do limit as x approaches 1 from the left. And see what happens with the limit as x approaches 1. Are they the same? Are they not the same? How is that going to impact my final answer? So if I'm just doing, and I'm going to write this down for the first one, left and right, but then I'll erase it because on the next example, that left and right is going to be totally different. So if I'm doing it from the right, there's nothing to plug in. I'll just say that it's equal to 1. If I'm doing it from the left side, I'm plugging into this first function. So I would do -1 plus 1, which gives me 0. Both of those limits exist, but they are not the same. So because they're not the same, the limit as x approaches 1 does not exist. They are going to two different places, so that is no good. Right, now I'm going to get rid of the left and right because we're changing, and we're going to look at a different break in the function. We'll look at limit as x approaches 2. So we'll do limit as x approaches 2 from the right, 2 from the left. The limit as x approaches 2 based off of those two answers. And then also we're going to add in f of 2 for this because we did have that option on the first one, but just something to look at because it's a little bit different here. So our first one, we're plugging in to the left side of 2. So that's where you're looking for the less than 2. That's going to be our left. And then where x is greater than 2, although it's flipped over in the order that it's written, this is the right side. Notice that x equals 2 does not impact the approach. That's going to be our f of 2. So when it says x equals 2, f of 2 is equal to 2 in that case. Now if I want to go from the right, I'm going to be plugging into the x minus 1 function. So I'll do 2 minus 1. That gives me an answer of 1. If I'm coming from the left side, again, that one doesn't have anything to plug into. It's the horizontal line of 1. So we'll just write the answer for that. Don't forget, though, I know this is very simple work, but you do want to show which function you're plugging into, regardless of how simple it is. These are the same, so we can say that the limit as x approaches 2 is equal to 1. The only difference here is our function value and our limit are not the same. So this would be something that was removed, a dot, or a point that was removed from the function and plotted in a different spot. But the approaching for the limits is all the same. So the limit as x approaches 2 of f of x does not equal f of 2. That's one of the cases. So first case, limit does not exist at all. Second case, limit exists, but it's not equal to the function value. And then our third case, which I'm going to have as part C, we are now going to take a look at the limit as x approaches 3, because that is the other break in our graph where the function is changing. So we'll do limit from the right, limit from the left, the limit as x approaches 3 based off of those. See if it exists. And then also we're going to do f of 3. It's not as cut and dry, but we will be able to see what that is. Okay, so if you notice here, we have less than or equal to 3. That equal to is going to help us know which function to plug into when we're doing the function value. And this is our left side. And then when 3 is less than x, that's going to be our right side, because that means x is greater than that. So if I'm coming from the right, I'm plugging in -3 plus 5. That's going to give me 2. If I'm coming from the left, I will do 3 minus 1. Also gives me 2. And then our limit is equal to 2 as well, because those two, again, are the same. Now for f of 3, we are plugging into the one that has the equals, less than or equal to. So for that one, we would do 3 minus 1 again and get the value of 2. So in this situation, we have the limit as x approaches 3 of the function is equal to the function value. So it exists and it's equal. So what you want to take away from this is you can have these different situations. The limit might not exist. The limit could exist but not equal the function value. Sometimes people confuse the limit with the function value. They don't have to be the same thing. But in our last example, that you can see that they are the same. So they can be the same, but they don't have to be. All right, we're going to stop there. We have a couple more examples to do with the piecewise functions and the one-sided limits. So we'll do that in our second video.